In our last video, we talked about the electromagnetic spectrum and particularly the visible spectrum of light. And so hold on because we're going to cycle back to that to the end. But first, we're going to ask a question. When things get really hot, they glow. The later part of the 19th century, the late 1800s, it was a fair question about why those hot things glow. And essentially the explanation that came about for that was that when those things glow, they're glowing because of the vibrational energy of their atoms. And so if those vibrational energies are pretty slow, as you're heating things up, just before they start to glow, they're going to give off frequencies that are going to generate infrared radiation. And so you're going to feel the heat around a heated object. And if you continue to heat them, then they'll start to glow red. And they glow red because the vibrational frequencies of their atoms are equated with the frequencies of red light. As things continue to heat, well, then those particles are going to start vibrating faster. And as those frequencies increase, you're going to start giving off more and more colors in the spectrum. You're going to glow blue. Eventually, you're going to give off high intensities of a lot of wavelengths, and you're going to end up seeing things that glow white hot, you may have heard. All of this is an investigation of a thing called black body radiation. And in the latter part of the 1800s, the idea of black body radiation and the theories behind it had a huge problem. Black body radiation is looking at the three possible outcomes of electromagnetic radiation hitting matter. 1, it could absorb the wavelengths. 2, it might emit the wavelengths. And 3, it might reflect the wavelengths. A perfect black body reflects no wavelengths. It absorbs all, it emits all. It's really not a super great name. It's called a black body because typically we only see colors that are reflected off of a surface. Because this object absorbs all wavelengths, it is called a black body, but because it also emits all wavelengths after it has absorbed them, black bodies glow. So it turns out it's not a super great name, but it's the one physicists use. Also, there is nothing in the universe that represents a perfect black body. Experimentally, there are some tricks. So one of the ways they study black bodies is you build a cavity, and inside that cavity you paint it with dark black paint, right? And then you let radiation only go in through a very small opening. That way anything not immediately absorbed will bounce around inside there and eventually be absorbed. And so you can look at the heat signatures, what happens to that object as it continues to emit or absorb and then emit more and more radiation. It turns out stars are also pretty good examples of near black bodies. And the really big issue in studying these is that classical physics, the physics of continuous energy, makes a certain prediction as things start to heat up. And that prediction is they're going to start emitting wavelengths of higher and higher frequencies, and eventually they're going to start emitting energy at infinite intensities. And that's impossible. You cannot emit more radiation than you absorb, and so it's a violation of the conservation of energy. Not only that, it means that you heat things up till they're glowing, and then once you get past that point, they're going to essentially melt the universe in the amount of ultraviolet radiation they would give off. And this prediction is known as the ultraviolet catastrophe. And so there's this graph that looks at what happens when you heat things at different temperatures. So each of these lines represents different temperatures of heating. So here we have something mostly giving off its heat. These are wavelengths down here in the form of infrared radiation. So it would just, if you put your hands around it, you would feel that it was hot. And as you continue to heat, you're going to push into emitting wavelengths, peak wavelengths at the red, which is going to give you glowing red hot. And then if we continue to heat, here we're at 5,000 Kelvin. Now we're going to be glowing with all of the colors, and this is like glowing white hot. Somewhere in between there, we'd kind of get that blue hot flame. And these lines represent what you see when you heat things. They absorb energy, they emit that energy at peak wavelengths, and then drop off when you get near ultraviolet. They don't emit very much ultraviolet light. But classical physics, and mainly this equation, which I don't ask you to make any sense of, predicts that once you heat past a certain point, you're going to start giving off infinite amounts of radiation. And that's not what happens. So a guy by the name of Max Planck in the early 1900s, who was studying a different problem, had an idea about how to fix the math, and it's essentially what he did. You know how when you get your answer wrong on a math problem, and so you figure out kind of how to change the equation, even though you didn't know how to set the equation up so it gives you the right answer? That's kind of what Max Planck did. He took that equation that predicted the ultraviolet catastrophe, and he changed some of the numbers and constants until the equation matched these curves of peak intensity of radiation as things heat. And so he changed the equation to look like this. Again, I don't ask you to make sense of that equation. What you do have to know about is this little thing right here, this H, which is called Planck's constant. And Planck's constant fixes the ultraviolet catastrophe problem, but it does it in a really weird way. So Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds, joule is the SI unit of energy, fixes the problem by saying, well, it might be the case here that the reason this doesn't work is that energy is in fact not continuous. Energy comes in discrete little bundles. Not every wavelength of light is possible. Certain wavelengths are not allowed by the universe. And so a good way to think about it is that classical physics tells us all of the energies in the universe are possible. Think about what we have here: long wavelengths, short wavelengths, and there should be an infinite number of wavelengths in between. What quantum theory tells us is there's not an infinite number of wavelengths because some of those wavelengths aren't there. And they're just not allowed by the universe. But what you have to look at is this constant 6.626 times 10 to the negative 34th is really, really, really tiny. So we can't really tell the difference. There are so many wavelengths that to our eyes we can't discriminate. And so everything looks continuous. And so we've talked about this idea of electrons being quantized. They can only have certain energies within the atom, but it's bigger than that. It's really the issue that energy itself is quantized. Only certain wavelengths of energy are possible, and from one to the next there's a jump rather than continuous possibilities. And so we'll continue to work with this idea in the next video.